Okay, so there's two things I need to mention before I start. First, exam one. You can take that with the night class. Wednesday, 2/12, so a week from tomorrow. That's at 6 p.m. in room S1326, or your class is Thursday, 2/13, 11. And just to the more conservative call here on the topics, we're only going to do the first two topics. So the stuff that we're talking about now is not going to be on the exam. So it's going to be harmonic motion, and waves. Okay. Any questions about the test? So if you look at the, on D2L, I don't know if you've noticed, but if you look in the course materials, I think it's in course materials. It might possibly be with the practice problems, but there's a list of equations. It's basically like all the equations for the whole semester. And all of the equations that are posted on that sheet will be available for the exam. I mean, I'll probably just chop it off, you know, so because there's so many of those equations that we haven't gotten to yet. So I'll probably only give the relevant ones, but I'll just put them right in that same order. So it's closed book and closed notes, but you will have all those equations and any conversions or anything like that that you need. And then second, we've been missing a lot of lab, but we do have lab this week. And by the way, lab is on sound waves and beats. So remember I mentioned that beats, when you have two waves that add up, at every time value you add the value of one wave to the value of the other wave, and you can get constructive interference where they come out to have a higher amplitude when you add them up, or you can get destructive interference where they sort of fill each other's gaps and you end up with a smaller wave, like a quieter sound wave. And the idea with beats is that since these waves are moving, since they have different periods, it takes them different amounts of time to repeat. So when you add them, you get parts that have constructive interference, followed by parts that have destructive interference, followed again by constructive interference. And that pattern of getting louder, quieter really fast is like a fluttering that you can hear. And that's called beats. And that's what this lab is going to be about. Okay, so who remembers what we were talking about last time without looking at notes? Yes, okay, so we started talking about the relationship between molecular motion and macroscopic behavior of a material. So I first talked about the sumo wrestling thing, that we're going to deal primarily with gases because it's much easier to calculate what's going on with gases. It's like talking about rubber balls bouncing off of each other instead of talking about people grabbing onto each other and pulling and pushing. And then I talked about temperature, and then I talked about what's that called? Thermal expansion. And so I talked about thermal expansion with solids, and then I talked about thermal expansion with liquids. What was the difference between those two? Smell? No. Yeah, right. Okay, so solids, a solid has like its own intrinsic length. Yep. And liquid doesn't have its own length, right? You can pour a liquid into any length of thing, but it does have its own intrinsic volume. So we went from talking about a change in length when the temperature changes for solids to a change in volume when the temperature changes for liquids. And now we're going on to talking about gases. And again, the way we talked about liquids isn't going to work for gases because gases don't have an intrinsic volume. You could take a jar of a gas and open it in a room and it would expand to fill the room. So we need to change what we're talking about again. So instead, thermal expansion will affect the product pressure times volume for gases. Okay, so if you okay, so think of like this is something we're going to think about a lot with thermodynamics. Imagine a piston in a cylinder. Okay, and the cylinder is filled with some amount of gas. Okay. As long as you make sure that the pressure on this gas is constant, then a certain amount of gas is going to have that same volume. Okay, so it's a relationship between pressure and volume in a gas now instead of just a volume like in liquid. And so thermal expansion for gases is going to look somewhat similar to how it looked for solids and liquids, but there are two new differences. So two differences for gases. First, remember what the equations for thermal expansion look like for solids and liquids. You had a relationship between a change in size and a change in temperature for both of those two equations. Now, we're not going to be talking about changes in pressure times volume and temperature. Instead, we'll be talking about instantaneous pressure times volume and temperature. This is a stronger statement. A stronger way of talking about it. We know more, we're going to know more about thermal expansion for gases than we knew about for solids and liquids. And then second, we're not going to need a coefficient of thermal expansion for each type of gas. Instead, we're going to have a single I'll say it as a constant of proportionality that works for all gases. And again, this is also a stronger way of talking about it. So again, we're going to know more about gases than we knew about solids and liquids. With these changes in mind, the equation for thermal expansion for gases is going to be the ideal gas law. PV equals nRT. Any of you who've taken chemistry have dealt with that. I need to give one more definition before I introduce the ideal gas law. And that is the mole. So think of a mole as an amount of a substance. And you can think of it as having two different definitions. Sometimes one is more useful, sometimes the other one is. You're going to have to use each of these at different times. So here are the two definitions. The first one is a mole is 6.022 times 10 to the 23rd molecules. Of a material. The second definition, so when we're doing calculations where we're talking about I guess this will be most useful when we're going between microscopic calculations of individual molecules, and macroscopic calculations where we're trying to figure out like a total energy in a gas or something. And then if you're talking about just totally macroscopic measurements, this is a more useful definition. A mole, okay, so if one molecule of a substance has a mass n in atomic mass units, and those are the ones I always just abbreviate lowercase u, then 1 mole of that substance has the mass n in grams. In SI units, you could also think of it as if one molecule has the mass n in atomic mass units, 1 mole has the mass n times 10 to the minus third kilograms. Any questions about any of this so far? Okay, so then the thermal expansion equation for a gas is called the ideal gas law. And the ideal gas law says a gas's pressure times its volume is equal to the number of moles times capital R T. And I'll tell you what all of these are. So P is the absolute pressure of the gas. V is the volume of the gas. N is the number of moles of the gas. R is called the universal gas constant. You can think of that as the constant of proportionality, like that's the gas's version of the coefficient of thermal expansion. And then the last one is, let me give you the universal gas constant. So the value is 8.314, and then the units are kind of a mass, joules over moles times Kelvin. But you could always figure out what those units were if you had to, just by knowing that this equation, the units have to work out. You know, so like if pressure was in newtons per meter squared, volume was in meters cubed, N is in moles, temperature is in Kelvin, then there's only one set of units that this can be. And then T is the temperature in Kelvin. So notice this, two things. First, always use temperature in Kelvin. And in fact, anytime you have an equation that doesn't talk about a difference in temperature in a physics equation, you're going to be using Kelvin because of the relationship between the Kelvin scale and absolute zero. Okay. And second, always use the absolute pressure. And let me tell you what that means. So if you measure pressure with like a tire gauge, okay, if the tire goes completely flat and you put the gauge in your tire, it'll read 0 psi or whatever units of pressure you're talking about. but you're not actually at zero pressure. What you're at there is, that's just saying that the tire has the same pressure as the atmosphere. There's no difference in pressure between the inside of the tire and the atmosphere. But there's a big difference between atmospheric pressure and zero pressure. One atmosphere of pressure, the atmospheric pressure, is equal to 1.01 times 10 to the 5th pascals. Okay. In other words, if you think of if you approximate the surface area of like a human body as 1 square meter, this says that there's a total force of what is that? 10,100. Oh no, even so, 101,000 newtons force pushing in on your body just from the atmosphere. Okay, so that's, well, I was going to say that's a ton of pressure, but actually this is much more than a ton, you know. That's a huge amount of force, unbelievable amount of force. So why is it that your body just doesn't collapse like an empty can, you know? The reason is that everything inside your body has atmospheric pressure too. So everything in your body is feeling this huge force from the outside pushing in that's being counteracted by a huge force from the inside pushing out. And the net effect is that you don't feel anything. And what you do feel is, so like if you, like when you take off in a plane, even though the cabin is pressurized, they only pressurize a plane's cabin to the equivalent of about 10,000 feet of altitude. So your ears pop and stuff because you have this, you still have this 1 atmosphere of pressure pushing out. Now you have a little less pressure pushing in. And so all of a sudden there's this strong force pushing out on all your organs and everything. And that's what, you know, can make your ears feel uncomfortable. That's also why, have you ever noticed that when they bring like potato chips around on an airplane, it looks like the bag's been inflated? You ever notice that? Look next time. It's like inflated fully, like, and why is that? Well, it's because the chips are packaged at 1 atmosphere of pressure, and then when you go up, even though it's percentage-wise, it's not a big difference in pressure when you go up to plane's cruising height. Now there's 1 atmosphere of pressure pushing out, a little less pressure pushing in, and so the out is winning. And if the cabin wasn't pressurized, you know, like if it was a cargo plane and these potato chips were in a, were just sitting underneath with 1 atmosphere of pressure on the inside and 30,000 feet of altitude pressure on the outside, so significantly less pressure, then the bag would just explode. you know, the pressure on the inside would win and the bag would explode. It used to be that airplanes, like where your luggage was, that part of the plane wasn't pressurized. And so if you forgot to like take the shaving cream out of your toiletries, you'd get wherever you were going and shaving cream would be everywhere because the cans would just explode. And it's all just because of that difference in pressure. So what was I talking about? So the difference between absolute pressure and gauge pressure. Absolute pressure, there's pressure everywhere and a lot of it. Gauge pressure is just saying how different the pressure is from one atmosphere of pressure. So here is the usefulness of the ideal gas law. If you know any three of the following quantities, pressure, volume, amount in moles, but you can figure out the number of moles from the gas, and I'll do some example from the mass of the gas. You could figure out the number of moles you have. I'll do some examples like that. And then the fourth one is the temperature. If you know any three of those four quantities, the ideal gas law lets you calculate the other one. Lets you calculate the fourth one. Okay, so here's an example. So say that we had like a tin can, you know, like a pop can, sealed and filled with CO2 gas. And let's say that the volume of the can is 0.0015 cubic meters. And let's say that the can is initially at a pressure of 1 atm. And a temperature of 20 degrees Celsius. Okay, so first, what's the mass of the CO2 in the can? And second, what's the pressure in the can if the temperature is increased by 200 degrees? And let me say something here. This is, so part B, by the way, when you change one or more of these quantities that defines the state of a gas, Changing one or more properties of a substance is called a process. When we talk about thermodynamics, there'll be, I believe it's 5 different kinds of processes. So we'll talk about a few different kinds of processes. This process, the one that we're going to do in part B, is what's known as an isovolumetric process, because we're changing the quantities inside without changing the volume. Okay, and all of these processes that we're going to talk about in thermodynamics depend on like what stays the same as we change the other ones. So this is called an isovolumetric process. Which just means the volume stays the same. Okay, so what do we know? The pressure is 1 atmosphere, which is 1.01 times 10 to the 5th pascals. Remember, pascals, pascals are 1.01 times 10 to the 5th newtons per meter squared, and that's the SI unit for pressure. Volume we were given is 0.0015 meters cubed. The temperature is, we want this in Kelvin. It's given in Celsius. So 20 plus 273 is 293 K. So we know 3 of these quantities, and that means we can use the ideal gas law to calculate the 4th quantity. So the ideal gas law says 1.01 times 10 to the 5th times 0.0015 is equal to the number of moles times the ideal gas, or the universal gas constant, 8.314, times 293. And you can see this will let us calculate the number of moles. And that gives you N equal to 0.0622 moles. Okay, so now if we can use the periodic table to figure out the mass of one CO2 molecule, then we can use this to figure out how many kilograms of mass we have. That's what we're trying to solve for part A. So one CO2 molecule has a mass of, carbon has a mass of 12U, and there's 1 carbon. There's 2 oxygens, and those each have a mass of 16U. And so you get a total mass of 44 atomic mass units. So the mass in the can is, so now what I'm going to use is the fact that 1 mole of CO2 gas has a mass of 44 grams. We have 0.0622 moles. So I'm just going to multiply 0.0622 times 44, and that's the number of grams. So 0.0622 times 44 is equal to 2.7 grams, or in other words, 2.7 times 10 to the minus third kilograms. And 2.7 grams isn't very much mass, but if you hold 2.7 grams in your hand, you can feel it. So even in like a pop can full of CO2 gas, there's enough mass in there to be noticeable. So now for part B.
Is there a way of doing a problem without changing the pressure from A2?
You would just need conversions for all the other, there is, but I don't have those conversions with me, right? I would say just always change it to pascals. Okay, so for part B, what changes here? The gas is sealed in the can, so we're not going to change the number of moles. We're not going to change the volume. It's an isovolumetric process. But the temperature is going to change and the pressure is going to change. And we know that the new temperature is 200 degrees greater than the initial temperature. So that's 293 Kelvin plus 200 Kelvin, so 493. And so PV equals nRT says the new pressure times the volume of 0.0015 is equal to 0.0622, that's the number of moles, times 8.314 times 493. And so pressure is equal to 0.0622 times 8.314 times 493 divided by 0.0015. Can someone calculate that for me? Okay, so 1.70 times 10 to the fifth pascals. So 1 atmosphere of pressure is 1.01 times 10 to the fifth. If you increase the temperature of the gas 200 degrees, it has the effect of, increasing it 70% basically. Increasing the pressure 70%. Oh, was it times 10 to the fifth or 10 to the sixth? To the fifth, okay. Anyone have any questions about either of those calculations? Okay, so remember that a change in temperature is the same Celsius as it is Kelvin. So an increase of 200 degrees Celsius is an increase of 200 Kelvin. The only thing that's different is the instantaneous temperature. Like an instantaneous temperature of 20 degrees Celsius is different than an instantaneous temperature of 20 Kelvin. But when you're talking about changes, they're the same. Any other questions? What do you think would happen if instead of, so the idea here was that this CO2 was sealed in this, I don't know why you would want CO2 sealed in a pop can. I don't know what that would be useful for. But say you did that anyways. And you did it at room temperature, 1 atmosphere of pressure. So we saw how much material was inside. How much material, like the mass of the CO2 gas, do you think it would be greater or less than what we have here if that CO2 was put into that can at 20 degrees Celsius, but at double atmospheric pressure? Do you have a feel for what would happen there? Same size can, same temperature, but now double the pressure. What would be the effect on the number of moles? Twice as much, yep. And so twice as much mass, yep. Okay. So the next thing that we're going to talk about is energy in a gas. And we're going to start talking about that in terms of the kinetic energy of individual gas molecules and its relationship to the temperature of the gas. The temperature of an amount of gas is proportional to the translational kinetic energy of its average molecule. In a way, you can think of temperature as being a measure of how hard the collisions are that the gas is making with the walls or with the temperature measuring device. If those collisions are applying big forces to the thermometer, then that's going to increase the temperature of the thermometer. The total kinetic energy, so first I need to talk about what I'm saying when I say that it's related to the translational kinetic energy. The total kinetic energy of a molecule is equal to the translational kinetic energy which is calculated as 1/2 times the mass of the molecule times the speed squared plus the rotational kinetic energy. And the rotational kinetic energy depends on two things: the rotational speed, how quickly it's rotating, and how spread out the molecule's mass is. And this part, the dependency on how far mass is distributed from, each chunk of mass is distributed from other chunks of mass, is going to be an important thing as we talk about energy in a gas. Okay. So the translational kinetic energy is just the 1/2 mv squared, but that doesn't measure the entire energy, the entire kinetic energy of a gas molecule. Okay, there's still, so we're going to have a relationship between this and temperature, but that's going to leave out this rotational kinetic energy, and we're going to have to deal with that. So the relationship between kinetic energy and temperature says the kinetic energy, and that overbar means the kinetic energy of the average molecule, is equal to 3/2 times kT so this is just the translational part, the translational kinetic energy of the average molecule. This K is called Boltzmann's constant. And it has a value of 1.38 times 10 to the minus 23 joules per Kelvin. And then T, again, is the temperature in Kelvin. So notice gas temperature doesn't tell us anything about the rotational kinetic energy. We're going to use this equation. So the, kinetic energy of the average molecule is equal to 3/2 kT for two things, really. The first is we can use it to figure out the speed of the molecules. So the kinetic energy, the translational kinetic energy of the average molecule is equal to 1/2 m and times a speed squared. This speed is called the root mean squared speed. Most people just call it the RMS speed. And it's not exactly the speed of the average molecule, but you can sort of think of it that way. It tells you what sort of a representative molecule's speed is. This m is, and this is an easy thing to get wrong, this m represents the mass of a single molecule. That's not the mass of the entire gas. Okay, so what we can do with this is if we know the mass of an individual molecule and we know the temperature of the gas, we can use the temperature to get the translational kinetic energy of the average molecule, and then use that to get the root mean squared speed. Yep. Yeah. RMS. Okay, so you can sort of see how this, I think, how this could be kind of a useful thing if you're trying to figure out microscopically what's happening with the gas. We have a way to take a macroscopic measurement, the temperature, and turn that into a calculation of how fast these molecules are moving. Okay, we don't have a way to turn it into how fast they're rotating, because that has to do with rotational kinetic energy, but we do have a way to figure out how fast they're going. The second thing that any questions about that one? The second thing that we'll use this for is to figure out the total translational energy in, some amount of a gas. And to do this, all you have to recognize is that the total translational kinetic energy is just equal to this number n times the translational kinetic energy of the average molecule, where n is the number of molecules. Okay, so say that the number of molecules, I mean, that would take a long time to count, right? Like, how many air molecules are there in this room? You could try counting, but you need a good magnifying glass, and that wouldn't really work. And you'd count one, and then it would move over here. It would be sort of a nightmare. So how do you calculate the number of molecules in a gas? What? Well, so the way you can do it is you can take a macroscopic measurement of the total mass of the gas, and then you have a relationship, from the periodic table how much, from the periodic table, the mass of each individual molecule. And so then you just do a division and you figure out how many molecules you have, So we can figure out the total translational kinetic energy in a body of gas by calculating the macroscopic mass of the gas and the macroscopic temperature. Okay. Now, what use is the total translational kinetic energy? You probably have an intuition that, there'd be more use to figuring out the total energy in the gas. Total energy is a kind of a more useful quantity to have. Well, it turns out in some cases, this is a good estimate of the total energy in a gas. So for monatomic gases, that's gases where the molecules are just a single atom. They don't join multiple atoms together to form a molecule. And the monatomic gases are the what are those called? Not the noble gases anymore. The halogens. Is that? I haven't heard it called that before, but all the helium, argon, all the the column all the way over on the right side of the periodic table. Inert. Oh, yeah. So now, right, I was thinking of inert gases. So now they're called noble gases. It's hard to make them react. And so all the noble gases, as a gas, they're just monatomic particles. They don't join together. So for monatomic gases like helium, neon, argon, and you can just keep going down the right side of the periodic table. Total translational kinetic energy is a good estimate of the total kinetic energy. And can you think why that would be? So think about it in terms of wherever I said, okay, so rotational kinetic energy depends on rotational speed and how spread out the mass is, okay? And so if you have monatomic gases where the molecule is just a single atom, the mass is much less spread out than if you have a molecule with 2 or 3 atoms forming it, right? And so that means that rotating at, say, the same speed, it's going to have a lot less rotational kinetic energy than a molecule that's made up of multiple atoms. Okay, so if you have a monatomic gas, translational kinetic energy is most of the kinetic energy of the gas. And you can use what you get here, the total translational kinetic energy, as an estimate of the total energy. For non-monatomic gases, would the total translational kinetic energy be an overestimate or an underestimate of the total energy? Under, yep. So in non-monatomic gases, you'll have this rotational energy that you can't detect in any way that's also adding to the energy. So translational kinetic energy is an underestimate of the total energy. Any questions about these? Okay, so here's an example. Let's see. What's the total translational kinetic energy in 1 cubic meter of nitrogen gas? Remember that air is basically 80% nitrogen gas. So basically I'm calculating what's the total translational kinetic energy in a cubic meter of air at 1 atmosphere and room temperature, 21 degrees Celsius. Okay. So what I'm going to calculate right now is the total translational kinetic energy in an imaginary box coming from the table to here, you know, and here, this big a box, okay? So there's several boxes this size in the room, you know, I don't know how many, 50, you know. And is this going to be a good estimate of the total energy in the air in the room, or an underestimate? Well, you just have to look at what type of gas it is. It's N2 gas, so it's non-monatomic. And so the number that I'm going to get is actually going to be less than the total energy in these air molecules. Okay. Okay, so what I have to do is, I know that the kinetic energy of the average molecule, the translational kinetic energy of the average molecule, is equal to 3/2 times K, 1.38 times 10 to the minus 23rd, times the temperature in Kelvin, so that's 294. And you get a value of 6.09 times 10 to the minus 21st. And what are the units? We're talking about kinetic energy, so, and everything's SI units. Yep, so this would be joules. The ideal gas law now says 1.01 times 10 to the 5th, so that's the pressure, times the volume is equal to N times the universal gas constant times 294. Can someone divide this? I have different numbers on mine. So what's N? So 1.01 times 10 to the 5th divided by 8.314 divided by 294. I think it should be right around 40, 41 or something. Okay. So now we have the kinetic energy for the average molecule. We have the number of moles. I'm going to use the number of moles to figure out how many molecules we have. And then I'm going to multiply the number of molecules times the, the energy per molecule to get the total translational kinetic energy. So N is equal to 41.3 times Avogadro's number. So 6.022 times 10 to the 23rd. And can someone multiply that one too? Okay. That's the number of molecules. And so the total translational kinetic energy is equal to 2.5 times 10 to the 25th times the energy per molecule, 6.09 times 10 to the minus 21. Can you multiply that too? Okay. And again, that's in joules. So we don't know what the total energy is in this meter square, meter cube box, but we know it's more than this because this doesn't this doesn't consider the the rotational kinetic energy. Okay, so my next question is this a lot of energy? Like, how can we put this in terms that we can sort of understand? Well, is that a lot of energy? And the way I'm going to do this, like answer that is, let's calculate how fast a bowling ball would have to be moving to have that much energy, okay? For it to have that much kinetic energy. So let's say that a bowling ball has a mass of 7 kilograms. Then 1.5 times 10 to the fifth, that's the total energy in the gas, is equal to the kinetic energy of a bowling ball. So 1/2 times its mass times the speed squared. And so 1.5 times 10 to the fifth divided by 3.5, take the square root of all that. Can you calculate that one too? This is the last thing I'll ask you to do. Okay, so 207 meters per second, or, you know, a little short of 500 miles per hour. So that seems pretty bizarre, doesn't it? I mean, that's just the kinetic energy, and it's an underestimate of the kinetic energy sitting on half of this desk above me. It makes you feel like there shouldn't be any like energy crisis. There's all this energy out there that we should be able to use for stuff, right? I mean, so say that this sitting in the room right now is enough kinetic energy to have 50 bowling balls moving at 500 miles per hour. That sounds like a lot of energy, right? I mean, imagine how much gasoline it would take to power a contraption that would make 50 bowling balls fly 500 miles per hour each. But it ends up being sort of a tricky thing. This really is true. There really is that much energy just sitting right here. But accessing that energy, not only is it hard, in a lot of cases it's impossible. And that's a lot of what thermodynamics is going to be about when we start talking about thermodynamics. Like, so there's this energy out there. When is that energy useful? What does it take to put it to use? So that's a little bit of a lead-in and also an example of how to use these calculations. Anybody have any questions about this? Okay, let's stop there. So see you on Thursday, and then the exam is a week from Thursday.